Swayam Prabha. Digital India. Educated India.
All right. Good morning. Good afternoon. Welcome back to the series of lectures we've been having on analysis and design of rigid pavements. We are currently in module 4. The module is on the mechanistic empirical design of rigid pavements. It's really the main part of the course that most of you are here for. So, in module 1, we had a brief introduction on rigid pavements. We learned about the different types of rigid pavements. There was JPCP, JRCP, CRCP, PCP. I had mentioned that JRCP is very rarely used and PCP is primarily used in specialized applications. So we don't really cover them in this course. JPCP is by far the most common type of rigid pavement. CRCP is also used a fair amount. So in this course, we basically focus on JPCP and CRCP. Now, in modules 2 and 3, we went through the analysis of rigid pavements. Module 2 was analysis of rigid pavements using classical methods. Classical methods are methods which are old. They are methods where you have, under some assumption, a closed form solution, a simple equation, a formula, if you may, which you can solve by hand using a calculator, at most with some kind of spreadsheet software. We learned about Westergaard's equations to calculate stresses and deflections for rigid pavements. We learned about Freiberg's theory. We learned about variations of Westergaard's equations, Taptabe's improvements to Freiberg's theory. So there were many different aspects of that. In module 3, we then started talking about the analysis of rigid pavements using the finite element method. More generally, they're using numerical methods. So I mentioned the fact that there are several disadvantages with using the classical methods. For example, classical methods make the assumption of large slabs. They make the assumption of the loads being circular or atmos square. They make the assumption of the subgrade having tension, being able to retain tension, etc. So there are several assumptions which are made, which eventually lead to several errors coming up in the design. Which is why in the last 30 years or so, in particular with the advent of digital computers and how quickly they've grown in capability and in reach, these numerical finite element methods have come about. Now, it's not to say these methods are perfect. As I have been mentioning, one of the most important things to understand in the finite element method is that first of all, your solution is going to be approximate. You are not going to get an exact solution. So we are getting an approximate solution, but with that approximate solution, we then know that we can overcome several of the assumptions which we discussed previously. For example, you can have a load which is of any arbitrary shape. You can have finite size slabs. You can have some non-linearity in the subgrade, that is, you prevent them from resisting tension, etc. So you can overcome a large number of these assumptions, but the shortcoming is that you will be giving up some amount of accuracy. And that is generally fine, because in rigid pavements, in construction, we generally have enough variability such that a small 1%, 2%, 5% error in design is as good as a small amount of variability in construction. So it really doesn't make too much of a difference. Now, one thing which I have emphasized in the previous lecture is the difference between analysis and design. So in module 2 and module 3, we talked about analysis. In analysis, you are given everything about the pavement. You are given the load. The load in particular is given, as we talked about, in terms of the weight, in terms of the pressure, and some type of shape of the load. So in module 2 and 3, we saw that you are given the load, you are given a pavement thickness, you are given the properties, or at least you can make some assumptions about the properties, you are told about the subgrade, and you're given information about temperature, for example. You are basically given everything, and you're asked to calculate the performance of the pavement. Performance, I mentioned, is basically in pavement engineering, it's related to stresses and strains. Rigid pavements in particular is related to stresses. Now, we can go one step further using fatigue theory, that instead of calculating stresses, we are calculating the effect of repeated applications of small stresses, which eventually we get a number which we call fatigue damage. and then we can sum up fatigue damage over the entire service life, over all the loads, over all the climate combinations, and then from there we would get cumulative fatigue damage. So we saw that in analysis we are basically given everything and we have to calculate cumulative fatigue damage. In the previous lecture, I told you that design is very different. In design, we don't have anything. We don't have a pavement. We don't know its materials. We don't know its structure. We don't know the traffic. We don't know the climate. We don't, obviously, because we don't know any of these things, we don't know anything about the performance. All we know is that whatever we design, the performance has to be within some acceptable limit, some acceptable threshold. What that limit and what that threshold is, we'll talk about as we go forward, but it really depends on the agency which is setting it. So, for example, what is an acceptable number of slabs which are cracked? There's no correct answer to that. It depends on who owns the road, what are the types of vehicles on the road, what is the economic cost of allowing the cracks to happen, etc. So in design, we know a little bit about our final answer. We have to somehow create or design a pavement which gets us to that final answer. And that's why in module 4, I took time in module 2 and 3 to explain analysis, because design is eventually an iterative form of analysis. We start by choosing some type of test section, some materials, we make a decision on climate, for example, and then we calculate our distresses and then we compare them to the performance. If the distresses are less than the targeted performance or the targeted threshold, it's an acceptable design. If it exceeds it, then we go back, we create a new test section, and by create I mean just do, it's a mathematical calculation. So we come up with a new test section, again go back and calculate distresses, compare it to performance or the performance criteria, etc. So analysis design is repeated or iterative analysis, which is why we spend such a large part of the course actually focusing on analysis. That said, there are key differences between design and analysis. One major difference, which will actually become the main focus of our lecture today, is on the load itself. So when it came to design, if you go back and look at the previous examples which we worked out, I always gave you the load. I would give you, for example, load of, for example, a wheel with a load of 80,000 newtons or 80 kilonewtons. And it has some tire pressure of maybe 1 megapascal, 0.8 megapascals, whatever. I gave you this information. And then from here, we went on to calculate stresses, etc. You can go back and review the examples which we did. Now, when we come to the design of rigid pavements, particularly using mechanistic empirical principles, this no longer applies. We don't have this information. What we do have is we have traffic, we have trucks, we have cars, we have bikes, we have autos, we have different types of vehicles on the road. How do we characterize traffic in such a way that we can use it for design of rigid pavements? That's basically going to be the topic of today's lecture. So in today's lecture, first of all, I'm going to talk about an old concept, which is easels, or what you might have learned as standard axes. So I'm assuming most of you have taken an introductory course on transportation engineering, so basic UG level course. Maybe you've also taken a course on design analysis of flexible pavements. In that case, you might have come across this term of axles, or sometimes what are called easels, equivalent single axle loads. You might have come across these terms. So I'm going to explain a little bit what it is, and I'll show you how it's purely an empirical concept, which we no longer use in mechanistic empirical design. It's still a very useful concept, but we no longer use it. I will then tell you what are the types of inputs, how do we actually characterize traffic in mechanistic empirical design. And there I will introduce what might be somewhat new terms for many of you, that is single, tandem, and tridem axles. There's also another category called quad axles, so I'll introduce that as well. And I will define something called an axle load spectrum and how it is obtained. As we shall see that for the mechanistic empirical design of rigid pavements, the axle load spectrum is ultimately what the main measure of characterizing traffic that we use. So I'll talk about what it is and how we measure it. Okay, so a little bit of revision from what we learned in the previous lecture. We learned that there are historically there are two very important design guides for pavement engineering in the US, but they also have significant effects around the world. So really, they are important all around the world. There is the AASHTO 1993 design guide. There was also an update in 1998, which updated quite a bit on uncertainty modeling for rigid pavement. So it is relevant to our discussion, but it's still generally called the AASHTO 1993 design guide. So the AASHTO 1993 design guide, we talked about it, was based on the ASHO road test for the most part. It was supplemented by some additional information over time, but still the bulk of the calculations was based on the ASHO road test. So this was purely an empirical approach. What do we mean by empirical approach? Well, for example, and this used to be what the Indian approach looked like. We might have, for example, on the x-axis, we might have some amount of traffic. However, we measure that traffic. We'll talk about that in a second. We might have some amount of traffic, and we might on the y-axis have what is the thickness of the pavement, of the surface layer, of the concrete layer. And generally, we would have some type of curve like this. Now, we'll have multiple curves. So each of the curves might correspond to, for example, different types of soils. So this might be, for example, a low CBR soil. So maybe this would have been CBR of 5, and this might have been CBR of 10. Again, I assume all of you've taken your basic course in pavement and transportation engineering, the introductory course in transportation engineering. So you're familiar with what CBR is. So I'm just going to use these terms under assumption. I do recommend all of you take such a basic course before you complete your degrees. Okay, so here is CBR. So this is what the curve might have looked like. So what we used to do then is, okay, we know that our soil has, for example, CBR value of 5. We know our traffic has some value. What this value is, I'll explain in a second. It has some value. So we would draw a vertical line thus, and we see, okay, it intersects the curve at this point. Now we draw a horizontal line. This might come out to, for example, 150 mm. So that's our thickness of our surface, 150 mm. This was how we did empirical. So really the empirical model was these curves. Coming up with these curves, now this is simplified. This is how actually it used to be done in India for quite a lot of time. The original ASHTO 1993 model is much more complicated than just doing something like this. You needed a spreadsheet in order to be able to do it. But nonetheless, philosophically, it was very similar along these lines. So this is what we called an empirical design. Coming up with these curves are basically built based on data from the ASHTO road test and some smart statistical model. ASHTO Pavement ME. So ASHTO 1993 was the big pavement design guide in its time. About a decade, actually more than a decade later, came the ASHTO Pavement ME design guide, which, as I've been mentioning, originally was called MEPDG. So that's the Mechanistic Empirical Pavement Design Guide. Brand name changed to Pavement ME. So I use the two terms, Pavement ME and MEPDG, fairly interchangeably. So please don't get confused and follow along with me. I mean the same thing, MEPDG or Pavement ME. So the Mechanistic Empirical Pavement Design Guide was actually based on mechanics. And mechanics, solid mechanics, what you've learned, strength of materials, solid mechanics, whatever you call that class, mechanics of materials. But basically, given a particular structure, given a particular material property to the structure, given a certain load which is applied, what are the stresses and strains? All of you, and I'm assuming you have a civil engineering background, so you must have taken that course on strength of materials and you've learned how to do this. Of course, the equations per se are somewhat more complicated when we're analyzing JPCP. They're not the same as, for example, analyzing stress in a rod. But fundamentally, it's the same idea that we are using some physics-based models and calculating stresses or fatigue damage in our case. Now, I did emphasize last time that we have not completely eliminated the need. When you talk about mechanics, you don't completely eliminate the need for experiments. We still have to conduct experiments. For example, you have to know the Young's modulus. You have to know the Poisson ratio. You have to know the flexural strength, for example. You have to know the compressive strength. So lab scale tests still have to be conducted in mechanics based or mechanistic based approaches. But what we don't need is large scale test sections to collect a lot of empirical data to generate these curves which I've drawn over here. What we do need in the mechanistic empirical approach is we need data collected on in-service roads. That is, it's not some special test section that has been built. They are existing roads with existing traffic. They've just been instrumented, they're surveyed, they're monitored regularly. So the data is collected on an existing road that is much cheaper than trying to build a test section every couple of years. So we use mechanics to calculate fatigue damage. And then we collect this data and using something what we called a transfer function, we create an empirical transfer function to convert the fatigue damage into some distress. The distress can be cracking, it can be faulting, it can be crack width, it can be punch out, etc. Those are for rigid pavements, and similar idea on flexible pavements. You could have rutting and alligator cracking, etc. So that is basically the approach of the Mechanistic Empirical Pavement Design Guide or ASHTO ME. You use your mechanistic models and you calculate fatigue damage. In the process, you may have to conduct some amount of lab testing, but we use these mechanistic models and then we create these transfer functions by collecting data from in-service roads, and then you use the transfer functions to convert the fatigue damage into distress, and then we compare the expected distress to a maximum allowable value, and see whether the design is acceptable or not. And if it's not acceptable, we go back and come up with a new design. So those are the two broad things, and we talked about this last time. Okay, today's lecture is on traffic characterization. So let me, before going into traffic characterization in Pavement ME, let me talk about how traffic was characterized in the AASHTO 1993 manual. By the way, this is still how it's done in India, even in the modern mechanistic empirical design for flexible pavements. We still use this particular concept, by the way. AASHTO 1993 defined the concept of standard axles, and sometimes they were also called equivalent standard axle load, so SAs or ESAs. A standard axle was taken to be 80 kilonewton. This is actually based on the AASHTO road test. So in the AASHTO road test at that time, 1956 to 1960, a typical axle load in India. So an axle is basically, it's a collection of tires. So you might have a tire like this and connected by an axle. So if you have the chance, you should do it, but please be safe when you're doing it and don't do anything illegal. If you actually go underneath a vehicle, not a moving vehicle, if you actually go underneath a car or a truck and you look what's underneath that, you will see that you have, of course, the two tires which you can see on either side. Sometimes you might have this, what is called a single tire. Sometimes you might have a dual wheel. For example, you might have two tires on each side, and you will see that they are connected along a shaft. That shaft is basically what turns. That's what the engine is turning. So the engine is turning the shaft. The shaft is in turn rotating these tires, and that's how the vehicle is moving. Of course, if you're a mechanical engineer, you would probably see I missed a lot of details along the way in this. I'm keeping it simple for this class. So this entire construction, the vehicles which are connected by the shaft, this whole thing we call as an axle. So when I say axle load, I mean the total load of the entire axle, which is distributed between the tires. We'll talk about distribution in a second. But what I'm basically, when I say axle, I basically mean the total tires which are connected using this shaft. And when I say axle load, I mean the total weight which is being borne by this entire axle, which consists of multiple tires. So back in 1956, 1960, the most typical axle load was an 80 kilonewton axle load inside the US. Now, again, 80 kilonewton, if we have a single axle with single tires like this, that is, if we have two tires, that means each tire is actually holding 40 kilonewtons. It's not always this case actually, but we'll talk about that in a couple of slides from now. So that means each is holding 40 kilonewtons. So this was considered the standard axle. The AASHTO road test was performed. The amount of damage then meant cracking, pumping, etc. So they actually measured these distresses. The amount of damage caused by, of course, the standard axle was measured, but they had trucks of a variety of axle loads. So they had down from maybe 20 kilonewtons, 100, 120 kilonewtons. So they have a variety of axle loads. And for each axle load, they actually measured what was the damage which was caused by the axle load. What was found back then is a very, very empirical approach. But what was found was that if the weight of an axle was W, and if suppose it was W and the axle of weight W created some amount of damage. And if we take a standard axle, which was 80 kilonewtons, and suppose we said that the standard axle creates a damage of 1. Again, damage you can think as sort of a fuzzy term. You could think in terms of slabs cracked or amount of pumping, etc., whatever it is. So if we just rescale the damage such that the damage of the so-called standard axle or this 80 kilonewton axle was 1, then it was found empirically that the damage of an axle of weight W somehow related to this fourth power law. That is, if the damage caused by the damage caused by any axle was found to be proportional to the weight of the axle raised to the power of 4. And it was declared, or it was defined, that the damage caused by an 80 kilonewton axle, which is called a standard axle, was 1. Forget, units don't matter, 1 of whatever, 1 unit of damage. And therefore, because this is proportional to 80 power 4, taking a simple ratio, what we find is the damage which occurred due to a weight of W, an axle weight of W, was actually equal to W over 80 raised to the power of 4. This is a very empirical relationship. This is what we call damage factors. So what was said that if we had an axle of weight 80, our damage was 1, regardless of units. if the axle had a weight of, example, 160, so double of that, then our damage, the damage is not going to be double. The weight is double. The damage is not double. The damage is actually 2 raised to the power of 4. So hence the fourth order law. So it would increase by 2 raised to the power of 4, which is 16. So it would increase by a factor of 16. So doubling the load increase the damage by a factor of 16. This is what was empirically observed. There is no fundamental derivation for this formula. It's just based on the data collected from the Asher road test. This is what was found, and that is then what was used to characterize traffic. So in the Ashton 1993 approach, all that was collected is you had to figure out what were the different axle loads on the road. So what proportion of axles were 80 kilonewtons, what proportion were 120, what proportion were 100, etc. They were all converted then into the number of repetitions of the so-called equivalent axle or standard axle, which is that if you had an axle of 160 kilonewtons, for example, it caused the damage of 16 times, and so we assume that one repetition of 160 kilonewtons was equivalent to 16 repetitions of 80 kilonewtons. That's basically how it was done. So all the traffic was combined into the so-called standard axles, so into one number called standard axles based on this empirical formula. By the way, this is still what we do in India in IRC 37 for the design of flexible pavements, and this exact formula, the fourth power law, is used, which was based again on the Asher road test from the 1950s onwards. We don't actually use this concept anymore in rigid pavements, but let's talk about that right now. So as I said, the concept of the standard axle or EASLs is purely empirical. It's just an observation that was made based on data which was collected. Many people actually use it now as some sort of a gospel or some sort of standard formula or a very rigorous mathematical derivation. It's not. It was just, even the term damage over there is a loosely defined fuzzy sort of word. It's just an empirical formula which was useful back then, but it is actually not used in pavement ME entirely any longer. I emphasize it is still used in India in IRC 37, which is for the design analysis of flexible pavements. It is not used actually in the design analysis of rigid pavements anymore, which is what we'll talk about in today's lecture and subsequent lectures. Now, I should add, although in pavement ME, this concept of standard axis is no longer used in design, it is still very useful for describing traffic on the road. So in India, for example, you might have come across this term in your undergraduate course, MSA, which is million standard axis. So this is just a quick number which tells you that if I have a certain number of amount of traffic, different axle loads, I can quickly combine them into one value using these standard axle factors. I can combine them into one value and express my entire traffic in my design life in terms of this unit of MSA or million standard axis. So although this approach is no longer used in mechanistic empirical design, you will still see it being used widely by engineers because it's a very easy and convenient value. So just keep that in mind, although this concept of standard axis of MSA is not actually used in analysis and design of rigid pavements anymore, it's still used in analysis and design of flexible pavements in India. But it's not used for rigid pavements in India, and in the US it's not used for either flexible or rigid pavements. It's still a very useful approach, so it's good to know what it is and how it's calculated. So it is still widely used in planning and administrative work, so you should have an idea of what it is, although we're not actually going to use it in subsequent calculations. Okay, so with that, we understood that was how traffic was characterized in the Ashton 1993 empirical approach. Still is used widely in India for flexible pavements today, but largely has been abandoned as a concept in mechanistic empirical design. So then how do we characterize traffic in mechanistic empirical design? What you may want to recall that we talked about this, the performance of JPCP is now evaluated. The modern theory we use is fatigue theory. That is, we want to see that given a certain amount of load, given a certain climate condition, what is the stress which is developed? So what is the stress? And if we divide the stress by the flexural strength, FCR, then this is what we call the stress ratio. So we saw that one application of a load will generate a repetition of a stress ratio. Different stress ratios will then have different number of repetitions. So we can actually create a table, stress ratio versus N. So you might have 0.1, 0.2, 0.3, etc. The number of repetitions might be in the thousands or the tens of thousands, for example. It depends on the application. What we saw is that in fatigue theory, based on stress ratio, we can calculate the NF, the number of allowable repetitions using what we defined as SN curves. So please go back to that lecture on fatigue theory where I described what is an SN curve. I showed you what this exact relationship is, how it's defined, what it looks like, in particular, what is an endurance limit. So please go back and review that lecture to learn that again. So we had these SN curves, and from the SN curves, we can get NF. So, and then of course we saw that for we can then derive N over NF, which we call the fatigue damage, and then we go on and do our calculations. So how do we actually calculate stresses? What we see is if we can calculate stresses, we can then calculate SR, and then the rest of the evaluation is fairly straightforward. You can actually program that on a spreadsheet. The real question is, how do we calculate the stress ratio, which in turn, how do we calculate stresses? Stress ratio or stress in turn depends on magnitude of the load. That's fairly obvious. The heavier the load we have, the more stress we expect, all things considered. It also depends on the position of the load. This we actually saw if you go back way back when we studied Westergaard's theory. And in Westergaard's theory, if you recall, there were actually three loading conditions. That was the edge loading condition, the corner loading condition, and the interior loading condition. And we saw that for JPCP, it's actually the edge loading condition which becomes critical. So what we see is it's not just the magnitude of the load which is important, it's also the position of the load which is important. So in calculating stress and thus stress ratio and thus fatigue damage, we need to know not just the magnitude of the load, but also the position, or let me use a different term at this point, the configuration of the load. Okay, that's in mechanistic empirical design, we really need, when we are trying to characterize traffic in a mechanistic empirical design sense, we really need to know two values. Firstly, we need to know the relative configuration of axles on the road. I'll formally define what these configurations are in a minute, but we need to know the relative configuration of the axles, that is spatially what is the shape and what is the size of these axles. And we also need to know the number of repetitions of each axle by weight. That is, how many 80 kilonewton axles do I have, how many 90, how many 100, etc. I need to know the number of axles. This particular thing, by the way, where if I plot, for example, the axle load, and if I plot, for example, frequency, and I might have a plot which might look like this. This type of a plot, which is showing the frequency of different axle loads, this is called an axle load spectrum. An axle load spectrum combined with information on configuration of axles is these two together are the fundamental ways in mechanistic empirical design to characterize and use traffic for the design of rigid pavements. You will notice that these standard axles, both in the US as well as in India, standard axles are not used in mechanistic empirical design of rigid pavements. It's still used as a administrative concept because it's an easy way to characterize traffic, but it is not widely used in design. Okay, so let's talk about axle configurations a bit. What I mean by axle configurations is how many tires do I have on an axle. So I already defined an axle is you have tires which are connected by a shaft that forms part of the propulsion mechanism of the vehicle. So you've got these tires or wheels and you've got this shaft, and this whole thing together is called an axle. So axle configuration means how many tires do we have? What is the length of the shaft? What is the spacing between the tires? So what are these individual spacings? Also, I think it's fairly obvious, but if you go out and look at any truck or any car, it's obvious that there will be more than one axle for sure. So a car might, for example, have two axles. You'll have a front axle and you'll have a rear axle. A truck might have more axles, and depending on the size of the trucks, you could have many more axles on the truck. Next time you're on the road, observe the number of axles on the truck. So not only are we interested in the shape and size of one axle, we may also want to know, for example, what is the spacing between axes. So are some axles closely spaced? Are some axles widely spaced? These are, by the way, I'm drawing axles over here. So there are other ones on this side. So are they closely spaced? Are they widely spaced? This is what we mean by axle configurations. The shape and size of an individual axle as well as the distance of the axles between each other for a given vehicle. Now, in theory, every make and every model of a vehicle has a unique axle configuration. You should know that there are many car and truck manufacturing companies in India. They come out with new models every year. Every time they come out with a new model, the axle configuration changes. Now, why exactly do they change it regularly? I'm not a mechanical engineer. My understanding is that when you change your engine type, when you change something with the aerodynamics, then for stability conditions, you have to actually move the axles around. So there is a particular configuration of axles which makes sure, for example, that the truck doesn't flip over if the engine has a particular load and a particular configuration. So mechanical engineers do these calculations. We don't really have to be concerned about it. But what we should understand then is that every year we get new vehicles which are released. Every year companies and people buy these new vehicles. Every new make and model of a vehicle has a unique axle configuration. So what that means is our traffic characterization seems to be a moving target. Every year the type of traffic which we have is changing. So what do we do for design purposes? We can analyze an individual vehicle, individual axle load, but when we're doing design, we have to take into account all the vehicles which are on the road for 20, 30, 50 years. Obviously, we can't do that directly or accurately. We have to make some simplifications. For design purposes, we actually come around with some reasonable classification of axle configurations. So we don't model every truck, every unique vehicle on the road by itself. We actually come up, we classify them into certain groups, and we say that, okay, within the group, here is the typical axle configuration. It's not going to be exact, but it's the typical axle configuration which represents a wide variety of make and models of vehicles on the road. We use those classifications then for characterizing traffic on the road. So what do I mean by classifications? I'll show you two figures, one here and one in the next slide. I'll show you how it's done in the US, and then I'll show you how it's done in India. They're actually fairly close to each other. So in the US, for pavement design purposes, they have a government body called FHWA, the Federal Highway Administration. So it is an actual government regulator, unlike AASHTO. So the axle configurations in the Federal Highway Administration, what the FHW does is actually came up with 12 classes of vehicles. So class 1 to class 4 that I've shown over here, and then class 5, 6, 7, 8, and so on until you get to class 12. So what you see here is class 1 is a bicycle. Class 2 is what we will call a passenger car. Class 3 is what you may call a pickup truck. So it's a car with a little space to hold some amount of goods, some amount of freight. Class 4 could be a bus. And then class 5 onwards, class 4 is particularly important, by the way. So you start with a bus and then you get trucks. You get these smaller trucks, and the trucks get larger and larger. And these additional things which are being added onto the truck, these are what we sometimes call trailers. So the truck might consist of this front part, which is actually driving. This is what you call a tractor. And then behind the tractor, you attach a trailer. That's also what we do in India, by the way. So in the Federal Highway Administration, you have these 12 class of vehicles. They go from bicycles and they go all the way to the multi-trailer trucks. In India, in IRC 3 particularly, there's a design code. We also have certain classifications. Our numbering scheme is different. So we actually start with type 2. What happened to type 1? I'll explain that in a second. We actually start with type 2, and within type 2 we have different types. So type 2 is a truck. We have type 3, which is another type of truck. We have something called type 2 S1, type 2 S2, type 2 2, etc. We've got type 3 S1, type 2 3, type 3-3, etc. So we have many different types also, but they are very similar. So for example, you'll see this is a multi-axle truck. This is also a multi-axle truck. This is a multi-trailer, multi-axle truck. This is a 2-axle truck without a trailer. So we do have these different configurations, whether in the US based on the FHW calculations, class 1 to class 12, or in India, type 2, type 3, and their subclassifications thereof. We have these different types of configurations. Now, I had briefly asked, where is type 1? Over here. So type 1 actually does exist. Type 1 is actually cars, bicycles, motorcycles, autos, what we would call light vehicles. The important thing to keep in mind is the axle configuration, what you noticed in India, it began with trucks or buses. So in the Indian classification, we do not actually have cars or bikes, motorbikes, or autos in this configuration. In the US one, they do have bicycles. They don't really have autos over there. So they do really have bicycles and cars, but these are not considered in design. So class 1 to class 3 are generally not used in design. The actual classification begins at class 4. And in India, we explicitly take into that account by completely ignoring the existence of type 1. The reason for this is as follows. if you actually do a mechanistic analysis, and we've actually done this in my research group, so I can say this definitively. If you actually see what is the axle load of a car or of a bike or of an auto, and you do the mechanistic analysis and you calculate what is the stress ratio which is developed due to these vehicles, it is negligible. The stress ratio might be of the order of 10 to the power minus 4, 10 to the power minus 5. It's essentially zero. And indeed, if you're using the concept of endurance limit in your fatigue curves, then at such stress ratios, you are not really developing any damage whatsoever. That is, the number of allowable repetitions is basically infinite. So the stress ratio for bikes and cars is actually negligible. It is well below the endurance limit if you're using the concept of an endurance limit. And therefore, in pavement design, we usually neglect these vehicles. So cars, bicycles, autos, light vehicles in general, we generally ignore them for the purpose of pavement design. We start our analysis with buses, and from buses then we move on to small trucks, big trucks, multi-trailer trucks, multi-axle trucks, etc. What you may want to pause and ponder on at this point is, if any of you have taken your basic course in transportation engineering, maybe you've taken a more advanced course in traffic engineering, you want to compare this approach in traffic engineering. In traffic engineering, we do not at all ignore cars, we do not at all ignore bicycles. In fact, we in India and in many parts of the world, we do have the concept of heterogeneous traffic and then homogenization of the heterogeneous traffic using a concept called PCUs, passenger car units. And then you've got passenger car unit conversion factors. So in traffic engineering, we are very much concerned about cars, about bicycles, about smaller vehicles, and we do assign certain values to them to try to homogenize the traffic flow. In pavement engineering, we completely cut these light vehicles out. We start our analysis with buses and then move onwards to light to heavy trucks. So that's sort of a major and an interesting philosophical difference between these two fields within transportation engineering. Anyway, moving on. So what I showed you now is we have different classes of vehicles. So in AASHTO, using the Federal Highway Administration's classification, we have class 4 to class 12. In India, we have type 2 and type 3, and within type 2 and type 3, we have 3 to 4 different subclassifications. These are all for buses and for trucks. Now, each of these vehicle classes, so now we've defined a certain class of vehicles. In each of these vehicle classes, then, we can have 3 important characteristics of that particular vehicle class. Those characteristics are the number of axles per vehicle. This is actually a very, very important parameter which is used quite widely in design. The number of axles per vehicle, the axle spacing, and the axle loads. So for example, let me draw a simple, I'll try my best to do a good drawing over here. So this might be a truck, and this might be the smallest type of truck. So this truck might look like this. Now this truck, how many axles does this truck have? This truck has 2 axles. Axle 1, axle 2. Sometimes this is called the steering axle because it is the axle along which is actually steering or driving axle. So at least for the 2-wheel drive, this is the axle that the engine is actually turning. Although in 4-wheel drive, it's not the case anymore. And the second one is sometimes what we call the rear axle. So the axle at the end. What is the spacing of the axles? Well, it depends. In this case, we have something like this. We could have a different truck. Let me try drawing this differently. We could have a different truck where you have an axle here, you have an axle here, and you have an axle here. So in this case, we have 3 axles. And so you have some spacing over here. So for 2-axle truck, this is our spacing. For 3-axle trucks, we have 2 spacings. And then individually, what are the loads on the axles? Generally, we assume that the rear axle is carrying most of the load. Particularly for 3-axle truck, we assume that these 2 rear axles are actually heavier than the steering axle. The steering axle is primarily holding up the engine, and it's holding up the driver. That, of course, is a negligible weight compared to the engine, but it's the engine and the driver and parts of the chassis which is being held up. Whereas the rear axle in the 3-axle case, the rear axle is what's actually holding the heavy load which the truck is actually carrying. So different axles might be holding a different amount of load depending on the configuration of the vehicle. So for each of these vehicle classes, what we would like to know is what are the number of axles per vehicle, what is the spacing of the axle, and what are the axle loads. In particular, this axle spacing is a very interesting and important concept because a lot of our design is actually built based on axle spacing. Based on axle spacing, that is not one axle but the spacing between multiple axles, we actually have 4 types of axes: single axis, tandem axis, tridem axis, and quad axis. These are very rare, quad axis. Okay. An axle, of course, as I previously defined, is a tire, the shaft, and another tire. There might be 2 tires on this side, so it could be a single tire, a single wheel axle, or it could be a dual wheel axle. So both options exist. So here is one axle. We could have along with that another axle over here. If you're talking about a single axle such that all the other axles are very far away, no vehicle is going to have only one axle. It's not stable, right? But even if suppose we have an axle and the next axle is very far away, we'll put numbers to these. So I'm just saying it qualitatively for now. But if the next axle is very far away, then we say that each of those individual axles is a single axle. If on the other hand, we have 2 axles which are relatively close to each other, I will put some numbers to what relatively close means. But if we have 2 axles which are relatively close to each other, then that combined system, these combined 2 axles together, is given the name tandem axle. So a single axle is one axle such that all other axles in the vehicle are far away. We'll define that in a moment. A tandem axle is 2 closely spaced axes. We'll talk about what closely spaced exactly means. But keep in mind, so for example, a single axle, what we call single axle dual wheel, SADW, that will basically consist of 4 tires, 4 wheels. If we have a tandem axle dual wheel means on each side of the axle we have 2 wheels. So totally each axle has 4 wheels, and because it's a tandem axle, there are 2 axles. So this actually cumulatively has 8 wheels. And a single axle double wheel actually has 4 wheels. We similarly have the concept of tridem axles. These are 3 closely spaced axles. So tandem axle is 2 closely spaced axles. A tridem axle is 3 closely spaced axles. I'll define again what exactly closely spaced means. It's just coming up in the next slide. A quad axle, we can go even higher. It's 4 closely spaced axles. Quad axles are actually quite rare to have. So it's not, you'll find guidance on it, but it's not really used very widely. Mostly it's single, tandem, and tridem, what we're interested in. Now, in theory, you can have a pent or a hex axle. In practice, we just don't find those. So single, tandem, and tridem are basically almost all the axle configurations that we have. Rarely in some very large trucks, you may have quad axles. You don't really have anything more than that, at least not yet in the way that trucks are being designed. As I mentioned, each axle can contain a single wheel or a dual wheel. Single wheel we might write as SW, dual wheel we might write as DW. By the way, single axle is usually written as SA. Tandem axle, as I wrote here, is shown as TA. Tridem we generally write as TRA. So we got, and so each of these 3, single, tandem, also quad axles, can be dual wheel, that is on each side of the axle, on each side of the shaft. Maybe we can have 1 wheel, which is called a single wheel, or we can have 2 wheels, which is called a dual wheel. So when we have a single wheel, we have 1 tire on each end, total 2 per axle. For example, this. So one axle has 2 wheels. Or when we have dual wheels, we have 2 tires on each end, so total 4 tires per axle. Again, I don't get into trouble, but if you have the chance to look underneath a vehicle, not a moving vehicle, if you have the chance to look underneath a vehicle, you will actually see all of this very, very clearly. And if any of you happen to be mechanical engineers, you would probably study much more detail on doing these designs, etc. Okay, so let me put some numbers into this. I kept using closely spaced vehicles. What does closely spaced mean? Of course, it is subjective, but there are some formal definitions which are used quite widely. This is the Indian definition, is very close to the US definition, so it either works. When 2 axles are spaced at most 1.8 meters apart, then we call them tandem axles. So for example, if here, again, let me try to draw this truck. If I have a truck as follows, where I have axle, thus. If I have that, let's say this distance is 1.2 meters, although usually the steering axle is ignored, but for now, bear with me, let's not ignore the steering axle. And let's say the next distance is 5 meters, for example. The fact that these 2 axles are within 1.8 meters of each other, so they're less than 1.8 meters apart, we will then group these together as a tandem axle. Now, these 2 axles, the distance between them is, it's not tandem, so it is more than 1.8 meters apart. since there are only two, there are not three axles, since there are only two axles, then we say that this last axle, then this becomes a single axle. So the first two are within 1.8 meters of each other, so they become a tandem axle. The next two are more than 1.8 meters of each other and there's no third axle available, then the last axle therefore becomes a single axle. Similarly, let's look at an example for tridem axles. Tridem axles is when the overall distance between the outer axles among a set of three axles is at most 3 meters. So the number here is 3 meters. What would that look like? So let me try to draw an example over here. So let's say we've got a truck like this and we've got 2, 3. We've got something. It's not an unusual configuration. Let's say this distance is some 2.5 meters. And let's say this distance is maybe, let's say 3.2 meters. This is all in meters. And then this distance might be, let's say 1.6 meters. What we see over here is then we have these two axles. They are spaced less than 1.8 meters apart, and therefore this might be a tandem axle. These two over here, the second and the third one, they are spaced more than 3 meters apart. Well, they're spaced more than 1.8 meters apart, so they're definitely not part of a tandem axle group. If you look at the last three, the outer spacing between, so spacing between the first one and the last one is 2.5 meters, which is less than 3 meters. And so we could say that these three are forming a tridem axle group. So in this case, the first truck I drew over here, this truck has one tandem axle and one single axle. This truck which I drew on the right, this has one tandem axle and one tridem axle. So in this way, we can actually we take our classification. So if it's FHWA, class 4 to class 12. If it's IRC, then it's type 2, type 3, and their subclassifications. For each of them, we can actually classify what are the number of single axles, what are the number of tandem axles, and what are the number of tridem axles on each of them. There are a couple of more terms that we should know. One term is called the wheelbase. The wheelbase is the total distance center to center. This is C over C. I hope you're familiar with this terminology. This is center to center. So the total center to center distance between the first axle of the vehicle and the last axle of the vehicle is called the wheelbase. In this example which I drew over here, then this distance, so 1.6 plus 3.2 plus 2.5. This distance is what we will call the wheelbase. Similarly here, 1.2 plus 5, that's 6.2. The wheelbase in this case is 6.2 meters. It's also an important number that we should know. So the wheelbase is the total center to center distance between the first and the last axle. The steering axle, I already defined this, it's the first axle. Sometimes in pavement engineering, we ignore the steering axle. I already explained why. The reason is sometimes, for example, in this on the right side, this steering axle this trailer might be completely detachable from the tractor. So the steering axle is actually just bearing the load of the engine and the driver. They are fairly negligible loads in comparison to the trailer, which is actually carrying the actual weight, the actual goods, which are much heavier. So sometimes in pavement engineering, depending on the application, we might just ignore the steering axle and we are only concerned with the other axles. The other axles, by the way, are sometimes called driving axles. Sometimes you'll also hear the term rear axles. So steering axle, driving axles. And finally, footprint is the contact area of the pavement, of the tire on the pavement. This could be circular, which is what Westergaard's assumption was. It could be rectangular, which is what we saw we do using, if you use iSlab, for example, we make the assumption of a rectangular load, and square is a subset of rectangular. It is actually in practice, it's more irregular in nature. So that's why we have, these are additional terms to keep in mind when we're talking about axle configurations. There is one more important term which I want to define, and that term is called wander. Okay, what does wander mean? Let's think of this axle, this truck driving along a road. So I've drawn here over a road and this is the direction of traffic. So this is what we would call a longitudinal direction. Okay, let's ask ourselves on this slab, where exactly is our axle? Let's just consider the tire which is closest to the edge. So it could be here, it could be a little away from it, it could be here, it could be anywhere essentially. So this one tire can be distributed all along the road. If vehicles are following the lane, now that's not what happens in India, but let's bear with it and we'll see how the Indian approach is to take this factor into account. But if vehicles are closely following their lane, then they will probably be following this line, which we call here the wheel path. It's going to be a constant value. Every vehicle is exactly following the vehicle in front of it. They're all going in a perfectly straight line. Then they will all follow this distance, which is called a wheel path. This wheel path in US experience has been observed to be roughly 450 mm from the edge, 457 if you want to be exact. So it's 450 mm from the edge. But as I'm sure all of you have experienced in India certainly, but also elsewhere, people don't travel in exact straight lines. You have a little bit of motion left and right. So vehicles go a little bit left, a little bit right as they travel. That slight lateral motion is what we call wander. So wander is the lateral movement of a vehicle within a lane. So what has been found in the US is, on average, the mean wheel path, the average position of the outermost tire is around 450, 457 mm from the edge. But there is a certain amount of variance. It's a normal distribution. So you have a mean wheel path, but there is also some normal distribution which is around this mean. And the standard deviation for this has been found to be roughly 250, 254 mm. So the actual position, remember what I mentioned, the stress which is developed depends not just on the load magnitude, but also on the position of the load. So we do really care about where the load is relative to the edge, because the maximum stress is going to come near the edge. We really care very much where the load is on the edge. So in the US practice, the idea is that the mean wheel path is roughly 450 millimeters, and there's a standard deviation of 250 millimeters approximately around that, which follows a normal distribution. How do we take this into account in pavement engineering and pavement design? We'll see that a couple of lectures later, but you should know this factor exists. Now in India, the truth is we don't follow lanes, right? So I'm sure all of you have experienced this. We don't follow lanes. The vehicles go wherever they want. They try to fill up the entire road instead of going in sticking to their particular lane. So how do we actually consider that type of behavior? That goes beyond wander. Wander is the lateral movement of a vehicle within a lane. If vehicles are not following their lanes, then there's no real concept of wander. Instead, we have a concept which is called lateral placement. How is that considered in Indian conditions? We will talk about that several lectures from now when we get into IRC 58 considerations. But for now, I wanted to just tell you what is wander, what is the concept of wander, and give you some numbers on how to calculate it. Okay, so we've studied what are axle configurations. That is, what are the different shapes and sizes of the axles, individual axle, as well as the distance between a group of axles, single, tandem, tridem, quad, etc. The last thing we have to look at is axle loads. So each of the axles is also carrying a certain load. That is the dead load of the truck itself. So that is the engine and the chassis and the different components of the truck, and also the goods which are placed inside the truck. Now in India, you have a wide variety of goods which are placed inside the truck. Many times you have agricultural products. You might have some agricultural products could be for human consumption. They could be for animal consumption. Many cases you will also see these heavy rebars, saria as we call it. So these heavy steel rebars for construction, they are being carried inside these goods. They are extremely heavy. You can see cement being carried, people's furniture being carried, etc. So you have a wide variety of types of loads which can be carried. In India, and actually in most countries, we do have a certain set of limits on this total loads. So in India, we do specify the maximum limit on axle loads. So what is the maximum load each axle can carry, as well as what is the gross vehicle weight? What is the total load that the entire vehicle is legally allowed to carry? These, by the way, these maximums, they're basically set for bridges. So when a vehicle is going on a bridges, we want to limit what is the total load applied on the bridge so the bridge doesn't collapse. So the motivation for providing both axle loads and gross vehicle weight is actually to take bridges into account. But it's also something we have to look at when we characterize traffic for designing JPCP, even if it's not on bridges. Occasionally, you might have some overloading, that a couple of vehicles now and then might be overloaded, and then they need some special permission to do it. So this rule does exist on axle loads. Now in India, whether it's followed or not very accurately is a different matter, but here is what the rules are. So in India, the rule is if you have a single axle, single tire, and tire wheel interchangeable word. So if we have what I wrote previously, SASW condition, single axle, single wheel, the maximum axle load allowed is 7.5 tons. Of course, this is tons. It has to be converted to kilonewtons, or you have to convert it. If this is in weight, you have to convert it into a force. So you have to convert it into kilonewtons, and I'll let you do that by multiplying with G, etc. Single axle dual tires, so as the SADW, that is allowed to calculate 11.5. You will see it is not double, right? It's 7.5 to 11.5. It's not double. Tandem axles and tridem axles, these are almost always dual wheel. So that's why it's not written explicitly. Tandem axles, which are on rigid vehicles, that is those which don't have a detachable trailer, they can carry a maximum of 21 kilonewtons. Tandem axle, which have tractors on them, have that is tractor and trailer are completely separable. They have 28.5. Tridem axle, 27. And the maximum gross vehicle weight specified in India is 49 tons for rigid vehicles, that is where you can't separate the tractor and the trailer, and 55 tons for articulated vehicles. There are also special rules for overloading. Now, whether the rules are enforced or not, well, that's a different issue. But you should know that these particular rules are defined, and this is the first time you're seeing this term over here, so let me define it. The Ministry of Road Transport and Highways, that is the nodal central agency. There are individual state agencies also. That is the nodal ministry which sets up all these rules. So that's where I'm getting these data from MORTH. All of this information, by the way, which I just summarized, you can also find in this code of practice called IRC3. I had already brought this out previously. So IRC3 is about vehicles on roads in India, and you will find this just about the same values you specified. Here you'll find front axle, rear axle, the weight on them, etc., and limits for the different types of classifications. Now, one important assumption is, generally in pavement engineering, we assume that axle loads are equally distributed across all the tires in the axle. That is if suppose I have a gross vehicle weight, for example, of 160 kilonewtons, and I have two axles which are, say, each of SASW type. So totally if I have two SASW axles, each SASW axle has two tires, and so totally I have 2 into 2 is equal to 4 tires. And so I assume that each tire is carrying 160 by 4. I'll show you an example for this in a second. It's carrying 160 by 4, which is equal to 40 kilonewtons. In practice, this is not the case. If you actually go and measure the load on a tire, for example, using a vane motion system, then you will find that different axles can actually carry different loads, and different tires can also carry different loads. That happens, for example, due to uneven distribution of goods inside a truck. You might be loading the goods on one side of the truck and not the other side of the truck. So different axles and different tires will actually carry an uneven distribution. But in pavement engineering, we ignore that problem and we assume that we have an even distribution, and then we move on with our analysis. So as an example, quickly I'll finish this in a few seconds. So if we consider a tandem axle, so this tandem axle dual wheel, total load of 200 kilonewtons. What is the load carried by each wheel? So tandem axle dual wheel basically looks like this. Totally we see here we have 8 wheels. So if we have 8 wheels, 200 divided by 8 is 25 kilonewtons. So the actual load on each wheel is quite low, 25 kilonewtons, but 200 kilonewtons as a whole for the axle is quite high. So the axle load spectrum is the proportion of axles on a roadway separately for each type of axle. So proportion of axle loads for each type of axle separately. This is what an axle load spectrum would look like. So for example, this is the axle load spectrum for single axles. This is from US data. It's defined for every 10 kilonewtons. At every 10 kilonewtons, we have what is the frequency of the axle loads. Similarly, we have it for tandem, which is spaced at every 20 kilonewtons apart, and we have it for tridem, spaced at every 30 kilonewtons apart. So what AASHTO does is it actually prescribes some typical axle load spectra for various parts of the US. So if you're in a certain part of the US, they've collected the data, and the Pavement ME software will then tell you what is the typical axle load spectrum which you can use for your design. You should theoretically collect the data for every individual project, but if you want to do a level 3 design, you can just collect the typical data. In India, unfortunately, we don't have this type of data. So in India, collecting traffic load data is actually quite complicated. And here is a little bit of code I took from IRC 58, which says that you can read it on your own later, but it basically says that for every individual project, you should be conducting a survey to know the axle loads and to know the traffic. So we unfortunately don't have any default values that we can use, which are ready-made values. Whereas in the US, they do have some level 3 traffic information, which you can use for design. Okay. So that was a lot of discussion on traffic. as you saw that for the empirical design, traffic was very easy. We just converted to standard axles and then we move on. For mechanistic empirical design, we have to know much more about the type of vehicles we have, the type of load we have, and the type of configuration. So it's significantly more complicated. On similar lines, climate consideration is also very complicated. So in the next lecture, I'll talk about how we model climate effects in the pavement ME or MEPDG. Thank you.